Good afternoon and welcome to the week 5 video. And I want to let you all know that for this particular week 5 video, you need to go ahead and use chapter 7 and chapter 8. Chapter 7 and chapter 8 for this lesson on cloud development and precipitation. So the chapter 5 would only apply to the 8th edition, and I know that everyone has the 7th edition right now. So utilize chapter 7 and 8 from your textbook for this particular video for week 5. All right, so we are going to talk about cloud development and precipitation in this video, in this lesson today. And we're going to start with the introduction on the importance of clouds. We did talk in a previous lesson about clouds in general, the types of clouds, moisture in the atmosphere, and now we're going to actually talk about the importance of clouds. So some of the main importance areas of clouds are they release heat to the atmosphere, to the surrounding air. And that's through the process of condensation. And you learn from the expression free CDs or a hot release that condensation tends to release heat to the surrounding atmosphere or the surrounding air. So clouds do release heat to the atmosphere, especially the cumuliform clouds, those ones that have the billowy, the marshmallow, cotton ball looking clouds. Clouds also regulate the Earth's energy balance. And we talked a little bit about that in the greenhouse gases when we talked about water vapor, which basically we're talking about water composing clouds, tends to trap long wave Earth radiation closer to the surface. And then also clouds indicate physical processes taking place in the atmosphere. The shape of a cloud will really tell you a lot. For example, if a cloud is growing tall and it's a big, puffy looking cloud, we generally know that the atmosphere is unstable. Whereas if you see more of a layer-like stratus cloud, more layered, then we generally know the atmosphere is stable. So that also, clouds do tell us the physical processes taking place in the atmosphere. All right, and clouds, generally when we talk about atmospheric stability, as we move into that topic now, clouds form as that air rises and cools in the atmosphere. Atmospheric stability is generally relates to a state of equilibrium. Okay, so if I were to say on a hot day with the sun shining, that shortwave solar radiation hits the Earth's surface. As a result of the heating of the surface, the air is less buoyant or lighter, and it wants to rise. And as that air rises, it cools. The air parcels cool and expand, and as that cooling and expansion happens, then those clouds tend to form. So generally, when we talk about state of equilibrium with atmospheric stability, air that rises is equal and opposite to air that sinks. So rising air is equal to sinking air. Adiabatic processes, this is the case when you have a parcel of air expanding and cooling as it rises, or it compresses, it gets smaller and warms as it sinks. So air expands and cools as it rises, an adiabatic process, and it compresses or gets much smaller and warms as it sinks. Now, adiabatic process refers to no interchange of heat with the surroundings. Okay, so everything is contained with the adiabatic process. All the energy transfer is contained within the air parcel itself. None of that energy or interchange of heat occurs with the surrounding air outside of the air parcel. The dry adiabatic lapse rate is 10 degrees Celsius per 1,000 meter rise in elevation, or perhaps we're talking about sinking air. And the moist adiabatic lapse rate is 6 degrees Celsius per 1,000 meter change in elevation. All right, so now this image shows you an example of atmospheric stability. If you look at the diagrams, the upper left, you see there's a gentleman sitting on top of that little ball labeled A. Okay? This is a case in the upper left of a stable atmosphere. And let's just say that ball we call labeled A is actually an air parcel in the atmosphere, okay? So we'll refer to that as an air parcel. So as that gentleman there is sitting on the air parcel labeled A in the upper left, that air parcel is situated basically in a valley in between mountainous or hilly areas, and that's exactly where that parcel is stable. So that parcel is not going to want to move sitting in the valley there in that dip between those two hills. It's in a stable situation. Now if I move over one to the right, the image to the right of the one on the upper left, so the upper middle picture there, you see the gentleman trying to push the air parcel labeled A up the hill. And as soon as he releases that, basically that parcel goes right back to where it started at A. So that represents stable equilibrium all along, those top three pictures. Because if you notice, even if you were to push the air parcel in the middle picture there in the top, that parcel would sink right back down to this original starting point. Okay? So that's a case where if you try to push air parcel rises or sinks and wants to return to its original position where it started, that is a stable atmosphere. The bottom two, however, you'll notice now this gentleman is at the top of the hill and we have a parcel labeled B. As soon as any force, let's say the gentleman here, he pushes it down the hill, that parcel will continue to move away from its original starting point, and that is termed unstable equilibrium, or simply that is an unstable atmosphere. So if I were to lift an air parcel, some force were to lift an air parcel, like a frontal system, or orographics, mountainous terrain, in an unstable atmosphere with unstable equilibrium, that parcel will continue to rise away from its initial starting point. Okay? So there's the difference between stable and unstable equilibrium. Now, in order to determine stability in the atmosphere, if we have that little tiny invisible air parcel, right, that little tiny parcel of air, if I am going to cause the air parcel to rise or to sink, again, as air parcel rises, it expands and cools. That's indicated here on the diagram on the left. And it compresses and warms. You see that red arrow with the down arrow there on the right. That's compressing and warming air parcels. So what I need to do, though, to determine whether my parcel will continue to rise or sink, which determines our atmospheric stability, whether it's a stable or unstable atmosphere, I need to compare my air parcel temperature to the surrounding air. Okay? So on the diagram here, we show an air parcel starting off at 30 degrees Celsius. That's its initial temperature close to the ground. That's about 86 degrees Fahrenheit. As that parcel rises and expands and cools, let's say at 1,000 meters, that air parcel is now at 20 degrees Celsius. And then up at 2,000 meters, you notice the temperature of the air parcel drops to 10 degrees Celsius. So in order to determine whether that parcel will continue to rise or want to sink, I have to know the temperature of the air parcel as compared to the surrounding environmental air. If the air parcel is warmer than the surrounding environmental air, that parcel will continue to rise because it's less dense or lighter than the surrounding environmental air. If the air parcel, on the other hand, is colder than the surrounding environmental air, that air parcel is going to want to sink. Okay? So determining stability, we need to look at what's known as the environmental lapse rate, which is 6 degrees Celsius per 1,000 meters on the left there. And then we need to compare it to the actual parcel temperature. Okay? We need to determine whether the parcel temperature is warmer or colder than the surrounding environmental air. So if you notice here, we're really showing you some differences in the changes in environmental lapse rates. So if on the left I have 6 degrees Celsius per 1,000 meter change in temperature, and on the right I have a 2 degrees Celsius per 1,000 meter rise or change in elevation, this is going to be an indicator whether you have a stable or unstable atmosphere. Okay? A conditionally unstable atmosphere is one in which if the air parcel is unsaturated, So unsaturated is a simple way to say the air parcel is not at 100% relative humidity. Okay? Unsaturated means it's not completely moist. If unsaturated stable air is somehow lifted to a level where it becomes saturated, instability may result. And there are differences between the moist and the dry adiabatic lapse rate. Okay? Conditional instability exists whenever the environmental lapse rate is between the dry and the moist adiabatic rates. So just keep that in mind as we continue. So I'm showing here in this diagram now the differences between the moist rate and the dry rate. So directly beneath the cloud in the diagram here, you see the dry rate is 10 degrees Celsius per 1,000 meters. And then once you reach the base of the cloud, that is known as the condensation level. So condensation level is the point at which you reach 100% saturation or 100% relative humidity, and your water vapor condenses into a liquid form. So that's where you see your cloud base at, your condensation level. Okay? So below the condensation level, below that point of saturation, as the air parcel rises, it is known the air parcel is going to rise at the dry adiabatic lapse rate of 10 degrees Celsius per 1,000 meters. Once you reach a condensation level or the cloud base, your air parcel will then change and rise at a moist rate, the moist adiabatic lapse rate, which is 6 degrees Celsius per 1,000 meters. And so look at the blue bubble and notice the changes. On the left here, also notice there's altitude in meters. So my altitude in meters there on the left goes from 0 at the surface all the way to 4,000 meters up there on the left, upper left. Notice my blue bubble here, that denotes my air parcel and how it changes in temperature for every 1,000 meters, a change in height. So initially my air parcel is at 30 degrees Celsius at the surface. It rises 1,000 meters, cools at the rate of 10 degrees Celsius per 1,000 meters, and it cools down to a temperature of 20 degrees Celsius. That's that blue bubble there in the middle of the diagram. Okay? And then that parcel continues. Once it reaches that condensation level, the cloud base point, now the air parcel rises at what's called the moist adiabatic lapse rate of 6 degrees Celsius per 1,000 meters. So you notice how at 1,000 meters, your blue bubble there, the air parcel is 20 degrees Celsius. Then at 2,000 meters, it drops to 14 degrees Celsius. And then 3,000 meters is 8 degrees Celsius. And then 4,000 meters, it cools all the way down to 2 degrees Celsius. But you notice how it cools at a rate of 6 degrees Celsius per 1,000 meters from the cloud base at condensation level to the top of the cloud up to 4,000 meters. So you're comparing that blue bubble, that's your air parcel temperature. Now we're comparing it to the environmental lapse rate, which is 9 degrees Celsius per 1,000 meter, per a radiosonde data. A radiosonde is simply an instrument that is used to determine the temperature changes with height. Okay? A radiosonde is a special type of instrument that determines your temperature, pressure, and the winds with height. So let's look at 1,000 meters and notice that the condensation level, that blue bubble there, is 20 degrees Celsius. Now look over directly horizontally to the right where the environmental temperature is at 21 degrees Celsius. So in this case, my air parcel, my blue bubble, is less than the environmental temperature. It's 1 degree colder, so my parcel will continue to rise. Okay? So hopefully that makes sense. You have to compare the parcel temperature to the environmental temperature. Okay? We get the environmental temperature from a sounding, an upper air sounding via an instrument known as a radiosonde. If, for example, if you look at the comparisons at 2,000 meters, 14 degrees Celsius air parcel compared to 12 degrees Celsius environmental lapse rate, that's the environmental air. You notice that your air parcel is 2 degrees warmer than the surrounding environmental lapse rate. So I have rising air and warmer, 2 degrees warmer, and then up at 3,000 feet, you've got 8 degrees Celsius in that blue bubble there, the air parcel temp, compared to 3 degrees Celsius environmental lapse rate or air temperature. So that's the parcel is 5 degrees warmer than the environmental air. So that parcel will want to continue to rise. All right. Now, cloud development and stability. Let's take a look at that. The mechanisms responsible for cloud development include surface heating and free convection, uplift along topography, or a rising air up mountain slopes or mountainsides. That can result in cloud development. Widespread ascent due to flowing together or convergence of surface air. This typically occurs with what's known as mid-latitude cyclones, where you get a large rising air mass over greater horizontal distances due to the different vertical motion associated with those cyclones. And then uplift along weather fronts. Along fronts we have differences in air density, we have differences in temperature, and that results in air rising along surface frontal systems. As air rises, in any case, it's going to result in cloud development. Now, convection in clouds. Convection is simply the process where we have rising air motion, vertical air currents in the atmosphere from a heated surface below, colder air aloft, results in rising air. And keep in mind that some of Earth's surfaces are better absorbers and heat up quicker compared to other surfaces. Okay? The hot bubble of air is known as a thermal. This breaks away from the warm surface and rises, expanding and cooling as it ascends. As air rises, it cools and expands. Just keep that in mind. This thermal mixes with cooler, drier air around it as it rises and gradually loses its identity. Here are examples of how you have cloud development in association with stability. All right, as I mentioned in the upper left, this is an example of a heated surface. So you notice the air rises through the center up through the cloud on the upper left-hand diagram. And you notice how there's blue sky around the cloud itself in the upper left-hand diagram. That is because you have sinking air around the cloud. So this is why sometimes you get that clear blue sky in between cumulus clouds. It's because there's air that's sinking in between those individual convective cells where the air is rising. Okay, on the upper right, I'm showing a diagram of air and rising up the side of a mountain slope. This results in cooling and condensing of air and results in clouds on the windward side of the mountain slope. And then in the lower left, I talked about pressure systems. When you have an area of low pressure associated with a mid-latitude storm or cyclone, you typically get larger scale vertical motion or rising air, which results in a lot of times precipitation out of clouds. And then clouds also form due to the density differences between the different temperatures, colder air being heavier and denser than warmer air. In the bottom right hand image here, I'm showing you lifting along weather fronts. Okay. Now, topography in clouds, keep this in mind. Actually, I got to go back one. Okay, I'm going to go back to this one real quick. Just showing you again this convective cell, how air rises from the heated surface below. And then you see the blue arrows. You see these blue arrows that are descending or sinking around those convective where the air is rising. That's why you get that blue sky in between cumulus clouds quite frequently. You'll notice a condensation level in this picture as well. You notice that's where the base of the cloud is at. Now we can move on to the next one. I kind of skipped that one and wanted to go back and make sure and show you that. Now, topography in clouds. When we talk about topography, we talk about changes in elevation with land. Okay, so we're talking mainly around hills and mountains. If you live near a hill or mountain, you're probably very familiar that sometimes you see clouds just covering the top of the peak perhaps, or one specific side of the mountain, and then it's clear on the other side. This is due to orographic uplift. When the wind blows against a mountain, it cannot just simply penetrate and go all the way through the mountain. Instead, the air's got to go, it's forced to rise. The wind's blowing against that mountain slope. On the windward side, the air is forced to rise, and as it rises, the air, it cools and expands and eventually condenses. The temperature of the air parcel cools to the dew point, and you get 100% relative humidity and saturation, and that's where you get your cloud base. Orographic clouds are formed through orographic uplift when lifting produces cooling and air is humid. So you got to have some moisture in the air as the air is basically rising. There's something known as a rain shadow, and this is usually on the leeward side of the mountain, where precip is noticeably lower and the air is often drier. And why is that? Because as air comes down from the top of the mountain down the leeward side, it generally tends to compress and warm. So really there's no surprise there. We already talked about that with the adiabatic process. As air sinks, it compresses, it warms, and that's what happens on the leeward side of mountains. And then we call that a rain shadow effect. And then lenticular clouds, these are clouds associated around mountains. They're usually at the peak and just downrange of it. And this is where precip is noticeable, this is a lens-shaped wave cloud. A lenticular cloud, some people have actually mistaken these clouds in mountainous areas for UFOs because they're very almond-shaped looking lenticular clouds, and they just look like they're stationary and not really moving. And then there's something known as a rotor cloud, which is a visible rising swirling air, and that's usually beneath the lenticular cloud. If you have any kind of aircraft around lenticular clouds or rotor clouds, definitely not a good spot to be for a pilot because there's a lot of turbulence around those type of clouds if you were to see those. All right, so here I'm showing you an example of orographic lift, showing you how as air rises, it's cooling. It cools initially at the dry adiabatic collapse rate of 10 degrees Celsius per 1,000 meter rise in elevation. Once you reach the condensation level or the cloud base itself, you go from the dry adiabatic collapse rate to the moist adiabatic collapse rate of 6 degrees Celsius per 1,000 meters. So if you notice, the cloud kind of hugs the windward side, the left part of the diagram here, the mountain. And then as air again comes down the top of the mountain, down the leeward side, it warms and compresses and dries out. And this results in a lack of clouds and mostly sunny conditions on the leeward side a lot of times. All right. These are the lenticular clouds and how they form. It's almost like a certain height above the mountain, you have a wavy type motion. The atmosphere is disturbed basically in wave-like undulations. If you look at, if the wind were to be blowing against the windward side, the left part of the diagram here that I'm showing, you notice that there's a wavy type motion to the air currents as represented by these brown and blue lines. And where the air rises, you have moist air, and you have air that rises temporarily. You get these lee wave clouds or lenticular clouds to form. And they look almost like they're almond-shaped. Or, like I said, some people have mistakenly identified them thinking they were UFOs and have actually reported and called these clouds in as UFOs mistakenly. Right below, you notice that rotor cloud is spinning right below all the lenticular clouds on the leeward side, a little bit of distance down range from the mountain, but the rotor cloud is closer to the ground. And again, lee wave clouds are known as lenticular clouds and also rotor clouds. These are very dangerous clouds because they have a lot of up and down motion and turbulence for pilots. Looking at the arrows, these blue and brown arrows and the wave-like motion, you can definitely see why a plane would not want to be around this type of pattern because there'd be a lot of bumps while passengers are in the plane, or a lot of changes in elevation over short distances, which you don't want to have that when you're a pilot. Now we're going to get into precipitation and precipitation processes. What is precipitation? It is any form of water, liquid or solid, that falls from a cloud and reaches the ground. And clouds are composed of many droplets that grow through the process of condensation. All right. So this diagram here is showing typical diameters of raindrops, cloud droplets, and then condensation nuclei. So the typical raindrop has a diameter of about 2 millimeters. The typical cloud droplet has a diameter of about 0.02 millimeters. And condensation nuclei, 0.0002 millimeters. So the condensation nuclei are very small, yet they're so very important. Now, how do cloud droplets grow and become heavy enough to fall in the form of precipitation? Well, we have two processes that produce precipitation in clouds. The first one is known as a collision and coalescence process, and this occurs when large droplets tend to overtake and collide with smaller droplets in their path. So as these larger droplets start falling from within a cloud, they collide in with other smaller droplets, which results in the larger droplets just basically absorbing and overtaking the smaller droplets. So these merging of cloud droplets by collision is called coalescence. And then the ice crystal process is when you have both ice crystals and liquid cloud droplets in a cloud, in clouds at temperatures below freezing. So you can actually have something in clouds known as supercooled water droplets, which is still actually a liquid despite being below freezing. And whenever you have ice crystals and water droplets side by side in the same cloud, there's going to be a collision, there's going to be a greater pressure, there's a difference in pressure between the ice crystals and the water droplets, and so you're going to have some growth of particles via that method. Now, here is an example of the collision coalescence process, showing you smaller cloud droplets on the left, and then you have larger cloud droplets begin falling within the cloud down, basically heading towards the ground, and these larger cloud droplets eventually overtake those tiny little smaller droplets, and they basically take in all the small droplets, continue to grow larger. So that's the collision coalescence part. This is when you have a liquid, the small little circular on the left there, those little droplets, and ice crystals side by side. Falling ice crystals may freeze supercooled droplets on contact through accretion, producing larger ice particles. And these falling ice particles may collide and fracture into many tiny secondary ice particles. All right, now we're moving on to cloud seeding and precipitation. So what was interesting, in the 1950s, there were many methods used by the U.S. government to try to figure out how to seed clouds with silver iodide or dry ice. There was actually, if you want to Google this, if you have some spare time, something known as Project Storm Fury. And this was a seeding experiment done by the U.S. government, funded by the government, to try to put a hole in hurricanes before they reach land. So the goal was to try to get this hurricane to kind of rain itself out. It's also been utilized in other experiments as well, as far as trying to get precipitation in areas with drought. And unfortunately, the results have been too sporadic to really say it works. So cloud seeding and precipitation. The primary goal of cloud seeding is to inject clouds with small particles that act as condensation nuclei. So I will say this, condensation nuclei, these are small little particles. It could be clay particles, it could be ocean spray, pollutants, and without condensation nuclei, if we had a completely clean atmosphere, water droplets tend to attract towards these condensation nuclei, but without them, with just a completely pure, clean atmosphere, it would be almost impossible to have clouds. So the overall goal of cloud seeding is cloud particles will grow large enough to fall out of the cloud to the surface as precipitation. And typically we use silver iodide, which causes ice crystals to form. The crystals come in contact with supercooled liquid droplets, and these crystals grow in size as water vapor deposits onto the silver iodide crystal. So here's an example of cloud seeding. You have regions of falling ice crystals. This is an example of an nimbostratus cloud trying to get precipitation to come out of it. Here is another example of cloud seeding, and you notice the areas below the cirrus clouds in the diagram, those little speckles, those are the ice crystals coming out. We're trying to seed the nimbostratus cloud to produce the snow beneath it. All right, and overall precipitation in clouds, this may begin only minutes after the cloud forms. If the cloud droplets, the water droplets within the cloud become heavy enough to where updrafts can no longer hold them, they can come out of the cloud very quickly. And this is initiated by either the collision coalescence or the ice crystal burgeoning process. And most growth is done by accretion, supercooled liquid droplets freezing at impact with snowflakes and ice crystals. That's accretion. All right, so precipitation types is next. So let's start with rain, then we'll move into snow and some other types. So rain is basically falling drops of liquid water Now, the difference between raindrops and drizzle. Drizzle has diameters of less than 0.5 millimeters, so very tiny. You ever notice on a foggy day how you see that mist just kind of floating? That's more of a drizzle. That's just kind of floating. Very small, tiny droplets, less than 0.5 millimeter in diameter. There's something also known as virga, which sometimes you'll see a streak of heavier looking, almost looks like a sheet of darker material coming out of the base of a cloud. And this is known as virga. This is evaporating precipitation before it reaches the ground. And then you have cloudbursts, which are excessively heavy showers, which you typically get with thunderstorms during the summertime. Now, snow. Some of us have seen snow and lived around parts of the country that has snow. This is frozen water falling from the sky. Most precipitation, believe it or not, starts off as snow because a cloud is well above into the upper atmosphere where the temperatures are far below freezing. So a lot of times all precip will start as snow, and then as it descends or moves outward, downward towards the ground, the temperature is warm and that snow melts into liquid. Important concepts: freezing level, the appearance, the fall streaks, the flurries, snow squalls, thunder, snow, and blizzard. There's something really cool with snow. You can actually get lightning and thunder with snow before, and that is called thunder snow. So here's an example, again, what I was explaining, how most precipitation starts off as snow. You see where the melting level is in this diagram. Anything above that melting level line is snow because the temperatures are below freezing. And then as the snow falls into below the melting level, this is where that snow quickly melts into rain droplets, and then you'll typically just have rain droplets at the ground. All right, and here's actual snowfall intensity. This is a snowfall intensity graph. Have you ever heard on TV before the TV weatherman say, ooh, there's heavy snow outside right now, or there's moderate snow? Or even if you look at the National Weather Service observations, you'll see light snow reported, or moderate or heavy. So this is what is used. So for light snow, your visibility is still greater than 1/2 mile. So we're using visibility to determine the intensity. Moderate snow has greater than vertical visibility of 4 miles, less than or equal to 1/2 mile horizontally. And then heavy snow is less than or equal to a mile. Okay? So real interesting, the different intensities of snow. Precipitation types. This chart here shows you average snowfall, annual average, so yearly average snowfall. And as we would expect, the higher values are generally over Canada, the purple shading colors, and the blues over the upper Midwest, the plains, the northern U.S., and then it gets less and less as we go further south, with, of course, correlating with the temperatures of winter. Now, what is sleet and freezing rain? These are two other forms of precipitation. Sleet is tiny, transparent, or translucent ice pellets that forms when a partially melted snowflake or cold raindrop turns back into ice when it falls through a deep, below freezing surface layer of air. And then freezing rain, this is a thin veneer of ice that forms as raindrops hit a cold object. So freezing rain is one of the most damaging weather precipitation types we have. And the reason it is because as the rain falls into a below freezing shallow layer near the ground, it generally tends to freeze on contact. And when it freezes on contact, it adds weight to power lines. Some of the more prolific power outages have occurred because of freezing rain events, because of the weight of the ice as that freezing rain falls, and as soon as it hits those wires or those power lines, it tends to freeze immediately, and ice tends to add weight, and that will basically cause the power lines to snap. So freezing rain could be very deadly, not only for power outages, it could be a major impact, but also accidents in the United States, people driving on basically ice rinks. All right, here's an example of the vertical temperature profile. When we talk about precipitation types, this is very, very important. Notice we have a nimbostratus cloud in the diagram. On the right, that red line there indicates your temperature curve from the ground all the way up into the cloud with height. You'll notice that the precipitation starts as a snowflake in the upper portion of the diagram, and the reason is your vertical temperature profile, that red line on the left, is below the 0 degrees Celsius line. If you go to the bottom there, bottom right, you'll see temperature ranged from -4 to 4 degrees Celsius. Well, 0 degrees Celsius is 32 Fahrenheit, or the freezing point. So if the red line bows to the left of that 0 degree line, then it is below freezing temperature. So that's why we have solid snowflake falling from the base of the cloud initially. Now, if that snowflake falls on the way to the ground and falls into an area or a layer of air which is above freezing, notice the red line there to the right. It's now above the 0 degrees Celsius as it curves to the right. This snowflake can melt into a raindrop. As that raindrop falls, however, now the temperature drops back below freezing in a certain level of the atmosphere, and this causes that raindrop to freeze and turn into sleet. So there's an example of a temperature profile in the vertical, and it's very important, especially in winter precipitation events, determining how the temperature changes with altitude as far as what precipitation an area is going to get. All right. Now we'll move on to a topic of more precipitation types, and we're going to talk about snow grains and snow pellets. Snow grains are solid equivalent of drizzle, so they're very small in diameter. They neither bounce nor shatter once they fall and hit the ground. Snow pellets are white, opaque grains of ice about the size of an average raindrop, a little bit bigger than grains, and they bounce, they're brittle, and they're crunchy when you step on them. And then graupel is ice particle accumulation with rime. And then hail. Hail is typically a warm summertime event. Warm summertime event because of the updrafts and downdrafts associated with thunderstorms. Hail are pieces of ice, transparent or partially opaque, ranging in size from that of small peas to that of a golf ball or larger. So when we hear reports of hail, we usually talk about nickel-sized, dime-sized, pea-sized, golf ball-sized. Sometimes softball-sized hail is extremely damaging. But hail is associated with the warm season thunderstorms. Here are your precipitation types. Again, just showing you the diagram of hail and how it forms. So summertime, think hail. Think thunderstorm cumulonimbus cloud. The red arrow indicates the updraft, the blue arrow the downdraft. And notice in the diagram here how your little hailstone embryo forms down the upper portion of the cloud. It becomes ice because it's above that 0 degrees Celsius freezing level, so it's below freezing at that point in the upper part of the cloud. And then the downdraft drags it down, so you'll get some kind of partial melting as it comes down. It'll be collecting water droplets, adding water droplets to it, and then it may get recirculated. If it's not heavy enough to fall to the ground, it may actually get recirculated around to the updraft side of the cloud and go back up again. And that layer of liquid on the outer part of the hailstone from the bottom of the cloud will go back up to the upper cloud and form another layer of ice on that hailstone. This is what a hailstone actually looks like. And you'll notice the concentric nature to it. It's concentric being circular. And you also notice that every layer there indicates a trip up and down through a thunderstorm cloud. So in this particular diagram of a hailstone, we've got the center, and then we go outward from that, and you see the ring-like structure. It looks like 1, 2, 3, 4, about 4 trips up and down through a thunderstorm cloud based on the number of rings outward away from the center of this hailstone. Measuring precipitation. How do we measure precip? Now that we know precipitation types, some of the processes involved in creating precipitation, we need to talk about the instruments used in measuring precipitation. And this includes rain gauges, and there's different types of rain gauges. There's the standard rain gauge, the tipping bucket rain gauge, the weighing type rain gauge. Also, we can measure precip through the use of Doppler radar and precipitation. The radar transmits energy towards a target, and then the return energy is measured and displayed on a colorful diagram, which you see typically on your evening TV weather on the news. The brightness of the echo is correlated with the amount and intensity of rain falling. So usually your reds and your oranges and your yellows are the heavier precipitation returns when we talk about using Doppler radar for precipitation. And then the lighter greens and even the blues are much lighter precipitation. So the Doppler, it measures speed of horizontal rain. So Doppler effect is really looking at the speed of the actual movement of hydrometeors within that radar sample. So here's an example of a standard rain gauge. So you notice that there's a measuring tube inside of the cylinder, the main center cylinder there. There is a collector, which is usually like a bowl shape at the top, which funnels the liquid when the rain's falling down into that little tube, the measuring tube. And if that measuring tube gets overflowed or filled up, let's say usually those little inner measuring tubes go up to about 1 inch of rain, but let's say you get like over 1 inch of rain, it will actually collect on the overflow cylinder, which is outside of it. You can actually join a network of precipitation observers out there, and it's called COCOROS. Google this sometime if you get a few minutes. If you want to become part of this exciting network of measuring precipitation, the COCOROS network is really a great resource. If you Google COCORAHS, COCOROS, COCORAHS. That's COCOROS, and you can actually join for free. And there's a link there to actually order a rain gauge and everything if you want to help contribute and do precipitation reports online. It's really cool. This is an example of a tipping bucket rain gauge. There's a lever that when the rain falls into the funnel at the top of this rain gauge, it will cause the bucket to, there's a little lever down below the funnel, and that actually dumps rain into the base of this bucket, and that will actually calculate your rain amounts. This is measuring precip with the Doppler radar. So the Doppler radar will send out these electromagnetic energy beams through the cloud, through the hydrometeors or raindrops, and it'll help determine the intensity. The Doppler radar sends out the signal, the EM energy. That energy then bounces off the raindrops and then returns to the Doppler radar unit itself and processes what type of precipitation you're looking at as well as the intensity. Here is an example of the Doppler radar, some of the displays that we see. This is a hurricane, August 27, 2011. This is a base reflectivity product on the left, and then you have the 1 hour precipitation total on the right. So Doppler radar can give you an estimate of precipitation as well as the current reflectivity, or how heavy the precip is falling at the present time. It's a real useful tool in meteorology. And the yellows and the oranges and the reds, those indicate areas with the heaviest precip on the left, and then on the right, those would indicate your higher precipitation totals in upwards of 1.75 inches there. Looks like we're looking at North Carolina here. Yeah, we are, from a hurricane that came in and made landfall. And then you also have these legends on Doppler radar for determining the different types of precipitation as well. Those will be usually on a weather map you'll see on the internet or online. You'll see, blue will represent snow, green will represent rain, and then perhaps like a yellow or even an orange. Some weather outlets will put orange for mix of rain and snow, stuff like that. So it's a really cool tool to be able to use, the Doppler radar. This just shows you a scan through a hurricane by one of the aircraft that actually their mission is to fly through these things and over the top at different altitudes and get a good estimate of the precipitation that's falling from these storms. All right, so in summary, today we talked about, in Week 5 video, we talked about stable atmosphere, and this is caused by either the surface air being cooled or the air aloft being warmed. So for stable atmosphere, I want you to think of this: warmer air aloft over colder air at the ground. So you have warmer air above, colder air, warm over cold. That is a stable atmosphere. If you want unstable atmosphere, you're going to have a cold layer above a warmer layer. So cold over warm for unstable. We used to joke around in a weather school I went to. We say, don't tip the cow. COW means cold over warm. So if you perhaps push a cow or something, it could tip easily. So in this case, cold over warm, don't tip the cow. That means that you have unstable conditions. Various forms of precipitation, we talked about that as well. Rain is just plain liquid moisture falling to the ground. Sleet are hard little pellets that bounce upon impact or once they hit the ground. Ice That can occur as a result of freezing rain. I talked about how significant that can be with power outages, as well as accidents on the highways and the roads. Very dangerous driving conditions. What appears to be wet pavement can sometimes actually be a layer of ice. Hailstones are summertime precipitation, generally from thunderstorm clouds, and then snow is obviously mainly a wintertime type precip event. This is where your temperature from the cloud all the way to the ground is below freezing, so that precip is going to remain snow all the way down on its journey from the cloud to the ground. All right, that wraps things up on week 5 video. I hope you enjoyed this lesson, and as always, please feel free to ask me questions if something doesn't make sense. I would be happy to elaborate further. Thank you for watching this video, and looking forward to continuing on with this course.